Okay, good morning everyone. So today is the 4th of March. It's the final lesson before we come back into school and actually get to meet you in person, which would be nice. So the starter that I'd like you to go through at the moment is what is Newton's third law of motion and define equilibrium. And then your keywords today are equilibrium and principle of moments. For the learning objectives, we've got define the term equilibrium, describe why objects at rest don't turn, and calculate the size of a force acting on an object that is balanced. So we'll be doing a bit of calculations today, but for now have a go at those two first questions. Okay, so the first question, what is Newton's third law of motion? He stated that every action has its equal and opposite reaction, and equilibrium we are going to go through in a moment. Okay, so here we have a balance. So we've got a student carried out an experiment to investigate the effects of placing varying masses at different distances from a pivot. But looking at this, they've only got one mass on there. So is that balanced, do you think? So you've got the anti-clockwise movement, so the rotation, and you've got the clockwise rotation. So this is not balanced because there's not a mass on the other side to weigh it out. And when an object is in balance, it is in equilibrium. So this girl on the left exerts an anti-clockwise moment, and the girl on the right exerts a clockwise moment, and they are both in balance, so they are in equilibrium. For this seesaw, you've got two people balanced on it. You've got 2 meters here, 1.5 meters there. This one is heavier, exerting more force because of their weight, but they are equal. So you've got 300 newtons times by 2, which is 600 newton meters, and 400 newtons times 1.5 meters, which is 600 newton meters. So they are in an equilibrium. So what I'd like you to do here is complete this set of students' results. Is the beam balanced? So say the student looked at several of those beams with the meter rule and different masses on each end, and then they measured the distance and the weight of each, and then they need to calculate the moment. So remember, the moment, got the equation triangle up here. Moment is force, or well, the force is the weight, so that's in newtons, times by distance. So you would do, for example, 50 times 5, and then that would be your newton centimeters. So pause the video here, have a go at that. In fact, actually, I'll do the first one with you. So the first one is 250, and that one is also 250 because you do 100 times 2.5, and then that one is balanced because you've got 250 on each side. So you've got 250 on the anti-clockwise side and the 250 on the clockwise side. So now you have a go at the last 3 questions, and then we will go through the answers. So pause the video here, have a go at those, and then come back. Okay, so let's go through the answers. So the second one, 25 times 10, that is 250. 50 times 5, that's 250 again. So yes, they are balanced. 25 times 20, that is 500. 50 times 15, that's 750. So that is not balanced because they are different. And the last one, 100 times 40 is 4,000. 75 times by 50 is 3,750. So they are not balanced either. Okay, and for this one, I would like you to try and calculate this yourself. So I'd like you to calculate whether this is in an equilibrium and what the calculations for each side would be. So you've got the numbers here and there for that side. Just be careful with this. Do not add them up at this stage. Add them up when you've calculated the answers. So have a go at that. I will write the answers down and then I'll talk you through it. Okay, so the first one, you've got 10 times by 2, so that is 20 newton meters. And then for the next one, you've got 8 times 1, which is 8 newton meters. 8. And then this one is 12 because it's 4 times 3. So now you add 12 plus 8, so 12 plus 8 is 20. So they are in balance. they are in an equilibrium. Okay, so now I would like you to calculate the clockwise and anti-clockwise moments on this crane. So you have your numbers here, so you've got 25 with a 4,000 Newton load, and you've got 5 meters with a 20,000 Newton load. So pause the video here, have a go at that, and we'll go through the answers. So if we go through the answers now, so it's 4,000 newtons times by 25 meters for the anti-clockwise moment, which is this one here, and then that one's the clockwise moment. So that is 100,000 Newton meters, and you do 20,000 times by 5 meters for the clockwise moment, and that is 100,000 again. So that is also in equilibrium. This is something that you would do in the classroom, but obviously we're not in the classroom right now. So I'm just going to talk through it as best as I can. So to measure an unknown weight, you would do a practical using known weights and balance beams and rulers and unknown weights. So you would determine the centre of mass of your beam and mark it as accurately as possible with a tape or a sticker. This can usually be done by balancing the beam on your finger, although a meter stick is ideal due to its existing scale. You would then set up your beam with your pivot towards one end and place a known weight appropriate for the beam used on a short length from the pivot, adjusting its position until the beam is balanced. So that is what you would do. So you've got your pivot here, you put the weight there until the beam is balanced. So you record the distances from the pivot to the final position of the weight, so from here to there, and then the distance from the pivot of the beam's centre to the weight used, so from there to there. And then ideally you should repeat that several times with the pivot in different positions. And you use the data obtained during the investigation to calculate the weight of your beam using suitable rearrangement of the calculation for principle of moments. And then you would then announce that the benchtop balance has now been located and used to confirm weight obtained by the investigation. So the benchtop balance being the scales that we would use to weigh an unknown object weight. So we would do that at the end to double check your calculations were correct. So how could the concept of a balance be applied to a wheelbarrow or a luggage trolley, do you think? So write down those ideas, look at this diagram for a good example, and then I will be checking your answers when you hand in your work. And for a little laugh, if you want to watch this video, this is when balance is not achieved, when there is not an equilibrium on a beam. So that is quite funny. So what moments are acting here? So let's see if we can calculate this. So we've got 3 meters there, 400 newtons, and 4 meters there. And obviously this is a very exaggerated cartoon because they've got very stretchy arms. So that is the clockwise, and this one is the anti-clockwise. That one is 3 times 400, which is 1200 Newton meters. And then this one is 4 times 400, which is 1600 Newton meters. So that is not in balance, that is not in equilibrium. Okay, so now we've got a scenario here. So we're going to look at this just to give you an example of how to calculate and how to rearrange the equation. So we have a total of 7 meters here, because you've got 4 on this side and 3 on this side, and it's 400 newtons of force. So that side has a larger force moment happening than this side. So you've got X and Y, so the equilibrium means that there's no acceleration of the beam, so the forces up and down must be equal. So there you go, these are the same sized arrows, just going the opposite way, because every force has its opposite and equal. So let's focus on force Y. So the moment is acting at point A over here and causing force at point Y. So A is 1200 Newton meters, and that is your moment. So let's look at this then. So we've got the equation triangle at the top, so moment over force times distance. What is the distance between the moment and the force? 7 meters. So to find out the force is the moment over the distance, so that is 1200 Newton meters over 7 meters, and that equals 171.4 newtons, and that is to 1 decimal place. So that would be Y. So let's have a look a bit further. So again, we've got the arrows pointing down and the arrows going up. So this one's 171.4 newtons. My animations have got a bit funny. So you've got 400 newtons minus 171.4 newtons, and that is 228.6 newtons. So that is the force of X. So X is 228.6 newtons and Y is 171.4 newtons. So let's double check the answer. So there is your anti-clockwise. So B is 1600 Newton meters, and you've got 7 meters. So 1600 divided by 7 is 228.6 newtons to 1 decimal place. So that is how you would do that. Now I'm going to ask you to do it yourself now. Okay, so this is the last task I'd like you to do. I will show you the answers after you've done this. So I would like you to draw, don't draw this accurately, just draw some stick people, and calculate forces X and Y. So you've got force X over here. You need to work out the moment of the force. So remember your triangle with moment over force times distance. And then you need to work out how much force is on each side. So the force of A and B. So look at what we did previously. If you need to go back and look through that again, you can do. And then draw this out and have a go at calculating it. And then we'll go through the answers. Okay, so let's go through the answers then. So we have moment equals 500 newtons, which is this middle number here, because that is what's acting on both of them. And that distance is 2 meters. So you do 500 newtons times by 2, and that is 1000 Newton meters. And the same for B. So you do whatever this is, so 500 newtons, and times it by 3. So that would be 1500 Newton meters. So those are the moments for each of these. So A is 1000 Newton meters and B is 1500 or 1500 Newton meters. And then you work out the force. So you do 1000 Newton meters for this side divided by 5, which is the total distance. And that is 200 newtons. And the next part you can do 2 different ways. So you could work it out using this method, or you could just subtract 200 from 500. So your force equals 1500 Newton meters divided by 5, and that is 300 newtons. And you can do that the same with 500 minus 200, and that is 300 newtons as well. So that is how you calculate this. And next lesson, we are going to look at parallelograms of forces, and that is going to be an in-person lesson. And we've got 2 more lessons before we do a revision lesson and then your test after that. So I'll see you next week in person.